So, not connected but here.
Yep, in presence. We struggled a lot to obtain his presence here, actually, because the consulate didn't want. It was like it's kind of difficult to have the visa.
Okay. Suspense until the end.
Suspense until the end. Yeah. Did you place in say sharing mode your screen? Okay, we got it. Yep. Okay. If you need a pointer, this is the third one. Okay.
Slides through this one.
Yeah, you switch through these ones. Okay. The candidate Dinesh Brindavanam investigated a new methodology to demise satellites during the re-entry. Satellites may not destroy completely during the re-entry. Methodology to ease let's say the dismantling of satellites is to add some energetic material on board the satellite. Dinesh developed a code to evaluate if this methodology is efficient and in which let's say extent. Dinesh, you have 15 minutes. Please go ahead.
Good afternoon to all. So I am Dinesh Brindavanam, a master student at the Department of Space Engineering. I am here to present my thesis on modeling thermite-aided spacecraft during re-entry. So first, let's start about the space debris. So anything that is left in the space by human over a period becomes a debris. So this can cause a lot of potential threats to the future mission. We can see like about 130 million pieces of space debris of about less than 0.1 centimeter orbit around the Earth. This can lead to a caseless syndrome, which is development of collision of consecutive objects can lead to further collisions. So some mitigation measures needs to be adopted. So it can be an active method or a passive method. So this helped me to start the problem statement. So there's a potential increase in the debris at the low Earth orbit. So we need to, one can adopt end of life measure for the low Earth orbit by exploiting the atmospheric re-entry. But however, for higher energy, higher melting point material, we cannot completely or partially demise the object. So we need to define a passive debris control method for future mission. So the idea is to introduce thermite and enhance the heat load during the re-entry. Does this really work? Let's see. So first, my thesis objective was can the introduction of thermites be an effective solution for complete demise of the satellites? Whether we can move from design to demise, the framework of design to demise to the, as a subset of design to demise, we can move to the thermite for demise. So to do so, I have developed a re-entry model embedded with the heat release from the thermites. This is the overall summary of this presentation. We start with the dynamic model and assumption, followed up by the mathematical model, model verification, parametric analysis and result, and finally conclusion and the future work. These are the main pillars of my mathematical model that I have developed. It contains of atmospheric model, geopotential, aerodynamic, aerothermal, ablation, thermite reaction model, and finally the kinematics. I have fully developed a numerical model during this thesis work, which has this following flowchart. It starts from the atmospheric model and it flows through it up to the kinematic model, and it is done using a ODE solver. Now we start first with the dynamic model. So the reference frame that was used for this one was a planet fixed and a local horizon frame. And the major assumption made was a 2D trajectory analysis with a ballistic re-entry configuration, point massing, and a single node thermal analysis. We start with a mathematical model. As the standard atmospheric and geopotential model was adopted, followed up by the geometric pointing modes. This particular has a configuration of the re-entry mode as face pointing, edge pointing, corner pointing, along with the tumbling modes. This is configured for 3 geometric shapes: the cube, cylinder, and the spheres. The aerodynamic model was first classified based on the flow regimes, based on the Knudsen number as free molecular, transitional, and continuum regime. This was further classified based on the subset of Mach number as well as the geometric features. And the last column shows the correlations that I have adapted for this particular model. This model helps us in computing the coefficient of drag. Similar to the aerodynamic model, the aerodynamic model also is classified based on the same flow regime and the geometric feature type. And the last column shows the correlationship that I have adopted for the modeling. Here in this particular thing, the flow property across the normal and the oblique shock are computed using a simplified curve fit for equilibrium gases. And this particular model helps us in computing the heat load generated during the re-entry with the exchange with the atmosphere. The most innovative part of my work was the slide which you see now. It is about the thermite reaction model. So the basic thermite reaction for chemical equilibrium is shown here, followed up by the proper parameters that have been used for the formulation. The thermite reaction model is basically, in my research, it was classified based on 2 approaches: heat-driven and thermite and the temperature-driven approach. And this is the heat-driven approach with the heat release profiles. So it starts like a step-like function, followed up with Gaussian, earlier triangular, late triangular, and center triangular. So once the code was developed, it is time to verify the model. So we started with the verification without the introduction of thermites. So this particular work, first the work was compared with the libs, and these are the initial parameters that were used for the simulation. In this particular work, we compare our results with the NASA's ORSAT and the ESA's CAR. So this particular work has a good aspect ratio ranges as well as 3 geometric shapes. In this, we can observe the maximum deviation was observed to be about 8%, less than 8%. Next, the work was validated, verified with the Raffaano's work, and the same like that. The initial condition are being shown here. In this particular validation verification, we consider the cuboid of CubeSat of 10 centimeter dimension, and this particular work helps us to verify the developed pointing modes. You can observe that the maximum heat flux for the edge pointing is like less than 17% of deviation for the maximum heat flux. Whereas for the tumbling mode, it is about 16% from the reference work. It compares only the maximum heat flux. The last verification was carried out with the Thrasholini's work, the initial conditions as follows. In this particular work, the 3 geometric shape was used for the comparison, in which the maximum surface temperature was used for the comparison. In this, we can observe the cuboid has a deviation of like less than 5%, whereas for the sphere it was less than 1%. So we can say that the maximum deviation for the validation was less than 17%, and it agrees good with the literature. Now the parametric analysis with the inclusion of thermite was carried out. The initial conditions are shown here. In this particular parametric analysis, a base case was considered as a cylinder made up of aluminium of a diameter of 0.25 centimeter, and this was the thickness. The variational property for the parametric study was varying the geometric shapes, surface thickness, material, thermite reaction model, and the thermite filling factor. The thermite filling factor is defined as the volume of mass that is filled inside a vacuum, inside the internal volume. This is the test matrix that was developed for this particular parametric analysis by varying one parameter at a time. A total of 20 cases were simulated, and the results will be discussed now. First, we'll try to observe whether the introduction of thermite is really effective. So once the thermite was introduced, we can observe that the object get demised 9 km earlier without the introduction of thermites. And these charts will be explained now. So we start with the relative velocity comparison. So in this particular graph, you can see the re-entry configuration. It starts from the time 0 and the time up to which it demises or completely reaches the ground surfaces. And the next chart over here shows the heat flux. The regular heat flux is something like this, whereas once we introduce a thermite, there is a sudden peak in the reaction. This helps us in ablating the model much quicker. Followed up by the surface temperature. You can see a steady steep increase in temperature, showing that the thermite ignites. The last chart shows the mass that gets ablated during the re-entry. So once we know the introduction of thermite is effective solution for the demisability, now we try to understand the heat profiles. So in the previous slides, I have told you there have been like 5 heat release profiles that have been adopted. It starts like Gaussian, earlier triangular, then the late triangle, center triangular. In this particular case, some interesting observations were made. So first one was the Gaussian profile tend to have the highest heat flux of more than thrice the base case. And all these heat profiles, although the profiles may be different, but all demise at same altitude. So from this, we can observe that the heat profiles are insensitive to the demise altitude. Next, we check the thermite filling factor parameter. What happens once we increase the thermite filling factor? So as we increase thermite filling factor, obviously the heat flux increases, leading to higher demise altitude. Now we try to change the geometric parameters. We try to understand what happens with the geometric parameters. First, we change the thickness variation. So once we increase the thickness of the object, then we tend to have a lower demise altitude. That means like the object tends to re-enter much more than once it was a thinner surface. Now we try to change the material and observe how effective is the thermite. So the green one that you observe is the base case, that is with the thermite, and the purple one is without the introduction of thermite. It can be observed that generally aluminium and graphite tends to demise naturally while re-entry. But in case of steel and aluminium, then we need to take some action because it does not completely demise. You can see that the mass of the object tends to remain after reaching the ground surface also. So some actions needs to be taken. We suggest like having a higher energetic material as the thermite reaction, or by increasing the thermite filling factor. And finally, we change the geometric shapes and try to understand the effects of it. In this particular case, we tend to have the sphere that generates the highest heat flux. Although it generates higher heat flux, we observe that it has very less demisability. It demises at lower altitude. This is because of the geometric constraint. The inner volume of the sphere is much lesser compared to the cuboid in which the thermite is filled. And finally, this is the conclusion of my work. I have developed the re-entry trajectory code that was verified for different geometric shapes such as cube, sphere, and cylinder, and for a wide range of sizes ranging from micro to macro. The introduction of thermite could be an effective solution to enhance the demisability. For thick surfaces or higher melting point material, we can tend to increase the thermite filling factor or have an higher energetic materials. And the future development of this particular work could be like improving the re-entry gas model, then introducing attitude estimator to move from a 2D analysis to a 3D one, then implementing a thermite reaction kinetics to find the reaction at different time steps. And finally, we can implement artificial intelligence to find an optimal mass that may be required, that optimal thermite mass that may be required to for different configurational geometry and different thickness. Here are some of the selected reference list of my work. And thanks for your kind attention, and I'm welcome for the questions.
The work has external reference.
Congratulations for your work. I have a couple of questions. The first one is that you can better specify your model, your item dynamics model with respect to the evidence model. It is basically an object-oriented code.
Yeah, object-oriented. It is an object-oriented.
Okay, and until now, let's say you have developed simple shapes, but you haven't yet considered, for example, function for multiple shapes.
Yeah, that is the next stage of work that can be carried out with the development of this one.
And then I have a question. The definition of the 3G26. Here you show very different behavior, demands, attitude, and so on, from different heat-driven profiles. Are you able then to really, in practice, create these different profiles? So, what is the confidence in being able to create a profile that then allows you to have actually that defined out?
Yeah.
What is the control capability?
Yeah, the control capability here could be like introducing a different configuration of like how you load a propellant in a different configurational shape that makes like ignition at a different rate, rather like loading it in a circular, like for a cylinder, not just loading it in a cylindrical shape, rather introduce a triangular shape in which the material will be loaded. So in this way, the profile can be in real time, can be generated also. Control would be like having a different shape in which the thermite will be loaded. The internal volume should be in a different shape to introduce this particular filling.
And this direction, let's say, how much is the actual controllability that then is really happens? So what is, for example, the you need to see what is the uncertainty in any one of the other parameters like the demise and so on, with respect to errors in what you try to achieve. Can you quantify that?
Yeah, so basically the heat profile here chosen was from the literature. Okay. So this particular profiles will be able to be modeled in real time also. The main way it can be modeled is not filling it in a particularly in a cylinder the full volume of the internal volume. Rather, we fill it in a different shape. This different shape needs to be studied, like whether the ignition of the thermite internal volume over a period of time could be in that particular profile or not. So, for example, if you consider a step-like function in which you tend to ignite almost at the same time and you maintain till the volume gets completely volume gets completely combusted, then the object completely demise. Whereas with Gaussian, there is a immediate heat flux. So the profile needs to be modeled in such a way of the internal volume in which the thermites will be.
Then I have one last question. I don't know if you have seen some work performed in a project with the Reg where they propose predefined fracture lines inside the spacecraft or an object, make sure that you control how you fragment the spacecraft entry, and therefore the spacecraft is divided in smaller shapes. So the question is, could this method be, let's say, applied to actually control these fracture lines?
Yes. So if there is a full satellite and there is a panel that is connected to the main frame, we can introduce a thermite on the joints, like on the nuts and bolts. That is the ultimate concept of this work. So once it is introduced, then we tend to break at the joint for simple shape, especially if you consider simple shape. Then we tend to break at that point. So the entire spacecraft can now become fragments. So the goal is to introduce at the joints, at specific joints where then some joints which cannot be replaced, like for example, if there's a steel bearing, so we cannot replace it maybe by other elements. So whether the introduction of steel bearing can still be demisable at that particular joint by introducing the thermite could be a feasible solution.
Then I don't know if you are aware of that word, but I don't remember now what was actually the mechanism. It's another way to structure this.
Okay. If there are no other questions,
I have a very minor curiosity, two curiosities, due to my ignorance on the field. The first one is in this slide. Why the Gaussian profile leads to so high a peak? In fact, I was imagining if you have a Gaussian, shaped profile, or a center triangle with a similar height, or similar, not the same, the total area should maybe made more or less similar. So why the profile of the peak flux is so higher, so much higher with respect to the other shapes?
Actually, the thing was related to this particular the time frame that we took for the ignition period. That is the thing that makes it the highest peak.
Okay.
But although the observation was whatever you ignited it immediately or take a time frame of this, still everything remains at same altitude. The observation was the profile. So the future you don't need to work too much on the profile to understand the divisibility altitude because it becomes a less sensitive parameter.
Okay. And the other question is concerning the shape. As you used, I would say, no special dependence of temperature, a lamp parameter approach. The influence of the shape is related to sharp corner, not body, so that's the influence of the shape.
Yeah.
Okay. Okay, thanks.
okay. Thank you. Facciamo la valutazione così puoi andare. Va bene, facciamo subito. Ok, thank you.
Thank you.
Good job.